This is lecture 2 from chapter 9 on chemical bonds. And next thing we're going to be looking at is chemical formulas. So chemical formulas just describe what elements are in a compound and in what proportions they are in. So this tells us what is actually in that compound. So the elements are going to be represented by their atomic symbols. So if you're not sure what element it is, you can always go back to your handy dandy trusty periodic table, because remember these guys are going to be listed on there somewhere. All of the elements that we would be looking at are going to be here. So what we're going to see when we write a chemical formula is that the metallic element that is in the compound or the leftmost element on the table is going to be listed first. So let's see what we mean by that. So here are some examples of some compounds. So we've got here sodium chloride, iron oxide, and carbon monoxide. So let's take a look at our periodic table. So we'll look first for sodium chloride. So if we look on our periodic table, over here is our sodium. So sodium is one of the metallic elements because remember these are our alkali metals and these are alkaline earth metals. And all of these guys here are transition metals here in the middle. So we definitely have our metallic element first. And then chlorine is one of the nonmetals way over here on the right-hand side. So definitely set up the right way. Let's see, the next one we had was iron oxide. So same thing, iron right here, one of the metallic elements, and oxygen over here, nonmetal. And then same thing for carbon monoxide. The leftmost element is first with carbon listed first, and then the rightmost element listed second with oxygen. So we're going to usually see, now there are some exceptions, but it's rare to have them listed in a different order. So pretty much most of the time you're going to see that metallic element listed first or the leftmost element if they're all nonmetals in that formula. Now, as far as telling us the proportions, we're going to use subscripts to tell us how many atoms of each element are present. So the ones that actually are up here that are in the example for the metallic or leftmost elements, these guys don't have any subscripts because for each of these, there's actually only one of each atom in the formula. So carbon monoxide, one carbon, one oxygen. Iron oxide in this version, one iron, one oxygen. And in sodium chloride, one sodium, one chlorine. So if there are no subscripts, we assume it's a 1. However, if it's more than 1, then it gets a subscript. So for example, this is why it's H2O. Hydrogen, and you get 2 of those, and 1 oxygen. Carbon dioxide, we've got 2 oxygens. Methane, the one we saw for chemical change, has 4 hydrogens. And then this one right here, this is a sugar. So 6 carbons, 12 hydrogens, and 6 oxygens. So these little subscripts, these lower numbers that are going to be found in the chemical formulas are going to tell you how many atoms are going to be found in that compound of that element. And it's going to be the number that follows the letter that is the number of those atoms. So valence electrons, we saw these at the end of chapter 8. We talked about these some. These are the outermost electrons, and these are going to be the ones that participate in chemical bonds, which is what most of this chapter is about. So for the A group families, so remember those are all of the guys on the periodic table that are not transition metals. So, you know, these 2 columns over here, and then all of these ones on this side. So we're leaving out the transition metals. We're not going to play with those guys. The number of valence electrons is the same as its family number or group number on the periodic table. So the exception is helium, and that's because of it being that period 1 element. So let's take a look back over at the periodic table. So that means for group 1 is 1a, so that means it has 1 valence electron. It has that 1 electron in its outermost level, just hanging out by itself. Group 2 is going to have 2. Group 3 has 3, 4, and so on until you get down here to group 8. Remember, group 8, these are the noble gases, so they're going to have 8 in their outermost level, except helium, because remember, helium is in period 1, that just for that first shell, which can only hold 2 electrons. All right. So which elements tend not to form compounds? Those would be the noble gases, because they actually already have a full valence shell. They already have that outer shell completely full. So they are not, those electrons aren't going to be looking for anybody to kind of fill in the spaces that are missing or get rid of them so that the next lower level is going to get filled up. So the noble gases are not going to tend to form compounds. The only way they do tend to form compounds is if we actually force them to create compounds. So what we have with these valence electrons is what we call the octet rule. Octet for 8. And that is the atoms are going to attempt to get an outer orbital or a valence of 8 electrons. So these outer rings want to have these 8 electrons. So for group 1, that group that contains things like sodium, they have 1 extra electron out in that outermost shell. So what they need to do is either get rid of 1 so that they then have 8 electrons in the next lower ring, or they'd have to gain 7 so that they could get 8 altogether. And so we're going to look at different ways that they can actually fill that shell so that they can get 8, or get rid of that 1 so that they have that next lower shell that's a full 8 electrons. So here, if you're having a hard time picturing what I'm talking about or forgot what we were looking at in the last chapter, so here's what I'm talking about. So here's that first shell that had those 2 electrons that it can hold. Here's the second shell with the 8. And here is that third shell, because we're looking at sodium, with the 1 lonely electron. So something like sodium would need to either get 7 to make this outer ring full with 8, or it's going to get rid of 1 so that it have 8 in this next lower ring, and it will be kind of what I think of as happy, or what we actually call stable. Because a stable atom is an atom that has a full electron shell with those 8 electrons. So electrons can either be gained or lost. We talked about this at the end of the last chapter. And the number of these electrons that they are going to gain or lose indicates what kind of bond they're going to be participating in to complete that orbital. So we looked at sodium before, and sodium is going to be one of the ones that's going to lose electrons, because it's a lot easier to lose this 1 electron than try and get or share 7 electrons. So it's going to lose this 1 electron, and if you remember, grab my pen, if we lose this electron, then instead of 11 electrons, we have 10, and that is going to give us a net charge of what? We've got 11 protons now and 10 electrons. So it's going to give us a net charge of +1. So that's going to create a positive, I don't have room to write it all in, but it's going to create a positive ion. So we're going to get, in the case of something like sodium, a positive ion because it's going to gain or going to lose that electron. If the valence shell is the opposite of sodium and it's almost full, so here we've got fluorine and it just needs one electron, it's going to steal that electron from somewhere and fill that outer shell. And here they've done the math for us. So we started with 9 and 9, but we've got one extra electron now. So 9 and 10 electrons, that's going to give us a -1 charge, which is going to give us a negative ion. Okay, it's just a little review from chapter 8. So as far as bonds go, there are 3 classes of bonds that we can look at. One is ionic bonds, so the bond that's created between ions and opposite charges. We've got covalent bonds. This is where instead of stealing electrons from each other to get that full valence shell, instead what they're going to do is they're going to share electrons in order to complete their valence shell. So we're going to see how that works and what kinds of atoms do that. And then the last one is a metallic bond. And so this is what a lot of the transition metals are going to be doing, and that is to create kind of a group of atoms that are closely packed together, and that's actually what you're seeing down here, where you've got the positive nuclei kind of hanging out, and they're going to share their electrons, and that's what these little red guys are, in a sea of the atoms all hanging out together to create this metallic bond. So metallic bonds, these are going to be found in solid metals, and these account for those properties we saw of the electrical and heat conductivity. And it's because of these loose electrons wandering around between being shared by the atoms, because those electrons can be knocked around to conduct electrical current and to conduct heat. And so that's why you don't see that with nonmetals, but you do with metals, because they've got this kind of sea of electrons kind of surrounding them to create that metallic bond. So I'm going to stop here, and I'll pick up in our next video talking about ionic and covalent bonds.